Hello students, welcome back. So we've been covering this module 5 wherein we're dealing with counters and A to D converters. In the first two sessions that we have discussed in this module, we started with looking at the decade counters, the presetable counters, and in the last class we did a synthesis problem wherein we designed a mod 6 counter using an FSM technique by simplifying the K-maps. So with that actually it will culminate the topic on counters. So what these counters, the reason that we've been doing these counters is counters become the building blocks for the topic that we want to discuss now, which we call as digital to analog converters and analog to digital converters. Now this is a session that we are going to discuss, and in this session we are going to discuss the variable resistor networks, the binary ladders, and the D2A converters and the performance parametric of D2A accuracy and resolution. So what are the learning outcomes for this particular session? Upon successful completion of this session, the students should be able to do the calculations related to variable resistor and binary ladder networks. We'll do one or two problems based on these as we go along, and then you should be able to study the various D2A converters and also calculate their resolution. Now before I actually start with this topic of D2A converters, A to D converters, let us first try to understand why is it that we require this conversion. Now the real world out there is going to be purely analog in nature. For example, if I were to sense the temperature, the value of the temperature could be 32 degrees, 32.1 degrees or 32.4 degrees, or it could be anything. It's an analog quantity. Suppose let us say I have to design a climate control system within, let us say, a agricultural sort of a hub wherein I have to maintain the temperature inside the hub at a certain temperature and humidity to ensure the maximum yield from my crop. Or it could be a case of having an air conditioner in your room, or it could be a case of air conditioner in your car. In all these cases, we need to have the systems which have to continuously monitor the temperature and either start the cooling, start the heating, or whichever way it is. But to do these calculations, we take the help of digital computers. Why? Because computers are very easily programmable. You can use the same program or the same hardware to control many different things. So what computers unfortunately do not understand the analog voltage. They only understand the language of zeros and ones. That is where the concept of analog to digital conversion comes. So if at all we have to take the input from the outside world and give it to the computer, you have to first convert it into digital. Likewise, on the output side, let us say a computer decides, okay, now I have to turn on the AC, or now I have to turn on the heater, or let us have to turn on the light. Again, the interface is analog in nature. We need to have a switch mechanism which is analog in nature. So a switch will only require an analog voltage. It could be a 5 volt, it could be a 6 volt, it could be a 200 volts or 230 volts as the case may be if it is an air conditioner or a heating system. So again there arises the need to convert the digital value to the analog value. So again we require digital to analog conversion. In our sessions here, we are going to discuss both these techniques of conversion, but we are going to start with digital to analog conversion. The reason being, analog to digital converters use digital to analog converters within them. So it makes sense for us to start with D2A converters first, and then we'll slowly move on to the A to D converters. So moving on then, let us start with the first problem that we are facing with. Let us consider a simple 3-bit system. So what is this 3-bit system? A 3-bit system means I am having a computer system or a digital system which can give me the outputs of 0, 0, 0 and all the way up to 1, 1, 1. Now my job is now I have to convert each of these 8 voltages or 8 values into analog voltages. So that is my requirement, like converting from digital to analog. As an example, what we can do is we can consider 0, 0, 0 as an analog equivalent of 0 volts. Okay, and on the other hand, we can consider the full scale value, that is all 1, 1, 1s, as an analog equivalent of 7 volts. We are taking 7 volts so that it is just for the ease of convenience, we can discuss it very easily. So if you make 0, 0, 0 as 0 volts and 111 was 7 volts. Now the question comes, what would 001 represent? What is 001 now? 001 is nothing but 1 LSB. Okay. So if you look at this particular table here, what am I trying to show is, I am trying to concentrate on this particular value over here. So wherein I call this as 1 LSB. What is 1 LSB? 1 LSB is the smallest increment in the digital value. Smallest increment, it starts from 000, so the next increment is 1 LSB. After 1 LSB, that is 001, if you want to increment it further, you have to add 1 to it. So 1 becomes my smallest increment for this particular system. So 1 LSB, how can you express that? If you look at these levels here, since we are choosing the levels as 0 volts and 7 volts, 1 LSB will be nothing but 1/7 of this voltage. What I am trying to say is 2 raised to 0 is your 1 LSB, and this is going to have a weight of 1/7. By telling weight of 1/7, the actual value would be 1 upon 7, right, into 7 volts, because the full voltage is 7. So if the weight is 1 upon 7, so the actual voltage is going to be 1 upon 7 multiplied by the full voltage. So this happens to be plus 1 volt. So what is my requirement now? My requirement is the smallest increment, which I call as 1 LSB, is now equal to 1 volts. Likewise, if I only look at the second LSB, what do you mean by second LSB? The bit which is to the left of LSB. Now as you can see, this has a weight which is twice the weight of LSB. So that means the weight of this would be 2 times 1 upon 7, which is nothing but 2 by 7. Similarly, if you look at the third LSB, which is nothing but MSB in our case, I am talking of this bit position here, which is at 100. So this particular MSB is going to have a weight which is twice the weight of the second LSB, which means it is having 4 times the weight of LSB. So that means its weight is going to be 4 upon 7. So if I were to ask you, what is going to be the value of the second LSB? So value of second LSB would be 7 times 2 by 7, because weight is 2 by 7, so I have to multiply it by 2 by 7. So that is nothing but 2 volts. Similarly, the weight of the MSB is 4 by 7, so the value of the MSB would be 7 times 4 upon 7, which is 4 volts. The beauty of this type of arrangement is, if you were to add all these weights, what I mean to say is, if you add 1 upon 7 plus 2 by 7 plus 4 by 7, all these weights add up to 1. So if we can have an arrangement which does like this, which we call as binary equivalent weights, then we can develop a system which can give you a binary weighted value. For example, if I were to find the value of 111, then what would be its analog voltage? Its analog voltage would be 4 upon 7 plus 2 upon 7 plus 1 upon 7 into 7 volts, which happens to be 7 volts, which is a full scale value. So if we are going to do a system which can convert digital to analog, we need to assign a weight to each of the bit positions. Let us move on from 2 bit to 3 bit, 3 bit to 4 bit. If I were having a 4 bit system, then what is going to be the voltage levels that I am looking at? In this case, again for the sake of simplicity, let us assume that the full scale applied voltage is 15 volts and the minimum value is 0. So in that case, the LSB is going to have a weight of 1 upon 15. The second LSB is going to have a weight which is twice the LSB. The third LSB is going to have the weight which is twice the LSB, and hence 4 times the LSB. So eventually the last one, which we call as a MSB, is going to have the weight of 8 upon 15, which again is twice the second LSB. sorry, third LSB. So if you add all these weights, again they sum up to 1. Now as a generic case, we can sum up this argument by saying for any n bit digital number, where n represents the number of bits, what is going to be the weight of the LSB that we require? The weight of the LSB is going to be given by this expression 1 upon 2 raised to n minus 1. For example, just to cross check the calculation that we have just now done, if the bits is 3, that is if n is equal to 3, what is the equation going to be? 1 upon 2 raised to 3 minus 1, which is nothing but 1 upon 7. That is what this table was telling us. Similarly, if the number of bits is 4, then the expression will change to 1 upon 2 raised to 4 minus 1, which is 1 upon 15. So for any n bit system, then the LSB weight is given by 1 upon 2 raised to n minus 1. So by this way, we can convert digital value to an analog value if we evolve a system based on binary weights. Now how is it that we can achieve this analog conversion from digital? We usually use what we call as voltage divider networks. Let us see one of them as we go in the next slide. So this slide sort of sums up your entire requirement. What is the requirement now? The requirement is I need to have a digital divider which is going to have a resistances. Okay, if I am dealing with a 3-bit system, then the inputs are going to be binary weighted 2 raised to 0, 2 raised to 1, 2 raised to 2, and I am going to have a resistor divider network which will eventually yield me a analog output. How are they going to be? If the digital input is all zeros, my analog output should be 0 volts. If the input is 1 LSB, which is 001, then its value should be 1 volt, and so on to the last one, where if all the bits are 1 at the digital input, its value should change to 7 volts. So this is a requirement that we have for our resistive divider network. Now let's move on and see inside this particular box of the resistive divider, how is it that we can implement them. There are two ways which we can do this. This is one of the first ways. Okay. So let's take time to understand what this entire slide is trying to tell us. So what are we having basically? We are going to have one resistor per bit. Okay. So let us identify where these digital inputs are. The first digital input is called the LSB. This is 2 raised to 0. The second one is 2 raised to 1, and this is where we have the MSB. Okay. That means for each binary input or binary bit, we are going to have one resistor. So if I am dealing with a 3-bit system, I am going to have 3 resistors. If I am dealing with a 5-bit digital to analog converter, then I am going to have 5 resistors. Now how are these resistors connected? Now these resistors are all connected in parallel. Okay. And how are the values taken as? If the value of the first resistance, let us say it is R0, so the LSB will have the smallest, the largest resistor, which is R0. The second LSB, the one to the left of LSB, is going to have the resistance which is half that of LSB. That means R1 is going to be R0 upon 2. Similarly, in this case, which is MSB, the value of the resistance is going to be half of its preceding resistor. So the preceding resistor is R1, so R2 is going to be half of R1. But what is R1? R1 is already half of R0. Therefore, R2 is going to be 1/4 of R0. So this way, the variable resistive divider network will have the resistances starting from the highest resistance at LSB, and thereafter every other bit is going to have its value half of its preceding bit. Okay. For example, 2 raised to 1 has R0 upon 2, 2 raised to 2 has R1 upon 2, 2 raised to 3 has R2 upon 2, and so on. So this way we proceed in this network. And what is the other load that we connect, and where exactly are we going to get the analog voltage? We are going to get the analog voltage where we short all the other ends of these resistors and connect it to a analog output. This output voltage is usually measured across a high resistance. The reason we take a very large load resistance is this ensures that it does not load the output. Okay. So, for all practical purposes, the resistance here is taken as so large that we can ignore it as an open circuit. Usually in practical converters, this high input impedance is given by op amps. We have already done op amps. We know that op amps have very high input impedance to the extent that we can almost ignore it as an open circuit. So, for all further investigations, we are going to simply ignore this and treat it as an open circuit and simply say that the analog voltage is at the node of all these resistances. So, how is it that we are going to measure this particular value? So, for that, let us again take the aid of an example. Now, let us say the inputs are 0, 0 and 1, which we have to now convert it into an analog voltage. Bear in mind, this 0 is your MSB and 1 is your LSB. So, essentially now we are trying to find out what is the value of 1 LSB. What do you mean by 0? 0 would nothing but as ground voltage. So, V2 is the MSB, I have connected it to ground. V1 is the second LSB, that also I have connected it to ground, whereas the LSB I am connecting it to plus 7 volt, which is my logic high input. Now, we have to find out what is the value of voltage VA. Now, to find this value of voltage VA, we use a bit of our network knowledge. There is something called as a Millman's theorem. Okay, Millman's theorem is used to find the voltage at node in a very easy equation. So, if you apply the Millman's theorem, which I am not going to cover here, but straight away we are going to use the technique of Millman's theorem. So, what does Millman's theorem actually say? We can see that in the equation that we have shown over here. VA is given as a ratio of current and conductance, which is 1 upon R. What is the current given by? V0 upon R0. What is V0 upon R0? The voltage applied at the first node divided by the resistance of that particular node, plus the voltage at the second node divided by the resistance at that node, right? That is what we are doing here, plus the voltage at the third node divided by the resistance at the third node. The entire thing becomes the numerator. Now, what does the denominator have? The denominator simply has the sum of all the conductances, which is basically 1 upon R. So, it is going to be the sum of all the conductors. So, it is going to be divided by 1 upon R0, 1 upon R0 upon 2 and 1 upon R0 by 4. This is what Millman's theorem says. In our case, the only difference is we now have to decide what are the values of V0, V1 and V2. Bear in mind, we are talking of analog voltages. You can't say, okay, V0 is 1, so I will go and put 1. No, V0 is digital 1, but what is the analog value? Analog value is plus 7 volts. So, bear that in mind. So, this becomes plus 7. So, it is 7 by R0. Now, these things become 0. So, I do not have to use these two expressions because they are both having the voltages as 0. So, the numerator then becomes 7 upon R0 and the denominator is sum of all the conductances. So, net you are going to arrive at an expression which will tell you that the LSB is nothing but 1 volts. If you remember in the previous slide what we said, we need to devise a resistive divider network in such a way that the LSB should yield me 1 volt and accordingly go on giving an increment of 1 volt for each additional increment on the digital value. This was the case when the input was 0, 0, 1. Now, let us try and see what is going to be a generic value for any given input. For example, the generic expression is given by this. For any digital input, the value at the output, which is the analog output, is given by this is starting from LSB. So, V0 2 raised to 0 plus V1 2 raised to 1 plus V2 2 raised to 2 and so on till we reach the MSB, and the denominator is going to be 2 raised to n minus 1. So, let us use this particular equation and try to solve one or two numericals so that we understand what exactly is the conversion from digital to analog. So the problem that we are going to take is, we are going to take the case of a 5-bit resistor divider network. So the input is 5-bit digital, okay, and I am going to convert it into a analog value, okay, and the example input, let us take it as 1 0 1 0 1, okay. Let this be the digital input. Now using a 5-bit variable resistor divider network, I have to now calculate what is its analog voltage. So in this case, you first have to identify what is the LSB and what is your MSB, okay, and you also need to know what is the applied voltage. So the applied voltage in this case, it is given as 10 volts, okay. That means the supply voltage is 10 volts. In the previous example, we took the supply voltage as 7 volts. Now in this case, it's a real practical circuit, so the applied voltage is 10 volts. That means logic 0 would be 0 volts, logic 1 would mean 10 volts. So that's the interpretation of this supply voltage parameter. So what is the analog equivalent now? So the generic expression was V0 2 raised to 0 plus V1 2 raised to 1 plus V2 2 raised to 2. We have to go on till where? Till we have 2 raised to, I mean if it is a 3-bit, we go for 0 1 2. If it is a 5-bit, we have to go for 0 1 2 3 4. So I have to go all the way up to 4, 2 raised to 3 plus V4 2 raised to 4. And what is the denominator going to be? 2 raised to n minus 1. So what is n in my case? N is 5-bit. So it is going to be 2 raised to 5 minus 1. Now all you have to do is figure out which of these is logic 0 and which of these is logic 1. In our expression, this is actually our V0, V1, V2, V3 and V4. But these are digital 0 and 1, we have to replace them by their analog value of 10 volts if it is logic high and 0 volts if it is logic 0. So this expression becomes V0 is 1, so I will make it as 10 volts, okay. 2 raised to 0 is 1 plus V1 is 0, so 0 into 2 plus next is V2, so V2 is again 1, but 1 is digital 1, so that is analog 10 volts into 2 raised to 2 which is 4, so I will write it as 4 plus again 0, V3 is 0, even though 2 raised to 3 is 8, it does not matter. Finally, V4 is 1 which is 10 volts and 2 raised to 4 is 16. The denominator is 2 raised to 5 is 32. So 32 minus 1 would be 31. So if we actually go and simplify this expression, we are going to get a value of plus 6.77 volts. Okay, I'm not going to do the maths over here. So what does that mean? If the digital input is 10101, if we are going to use a variable resistor network, the expression is used like this, applied, and then finally you get the value as 6.77 volt. Okay. So this is how you can go ahead and calculate the value of the analog output for any given digital input. This is a calculation which is expected to be known by the student. Now comes the question about the feasibility of this type of resistor network and what are the problems that are associated with this kind of networks. So if you can go back to our slide here and see what exactly is happening. Okay. So what is happening is each resistor was going on getting smaller and smaller. The largest was R0, R1 is smaller, R2 is smaller. Let us imagine we have a 10-bit converter. So if it is 10-bit converter, you can imagine the last resistor will be almost 500 times smaller than the first resistor. The first is the challenge of getting the resistors of equal value, means we need to have precise resistance values, because if the value of resistance changes, then the accuracy issues are going to creep in. That means I am not going to be able to calculate whatever is the theoretical value, the practical value may not be the same, because there are a lot of tolerances in the resistors. That is not the only problem though. Another problem is the relation with respect to the currents in each of these branches or nodes. What is happening is, at LSB the resistance is the largest, means the current is the smallest. By the time you come to the MSB, the resistance is the smallest but the current is the highest. That means what? Each successive node is going to have the currents in increasing order, to the extent that for a 10-bit case you may have the largest, that is the MSB node having a current 500 times the current of your LSB node, which is usually not a desirable thing to have in resistive networks. I would like to have a resistive network which will have almost similar currents through all the nodes, because I need to look at now the power rating of the resistors. The smallest resistor can be quarter watt, but the largest resistor, the largest node, let's say MSB, need to have a wattage of maybe 10 watts or 5 watts, or as the case may be. So that becomes very impractical to do that. So let us look at another scenario which solves this problem. Now that particular network is called as a binary ladder. Okay. What does a binary ladder have? Let's take time to understand this particular configuration. Here we are taking the case of a 4-bit digital to analog converter. Where are the 4 bits? We are going to start with 2 raised to 0. Bear in mind, this time we are going to have a LSB on the extreme left. Okay, students need not get confused. This time we are going to have 2 raised to 0 on the extreme left. So LSB is here and MSB is on this side. Okay, so that's the only variation. Whereas in case of a variable resistor network, you had the LSB on the extreme right. So that need not get confused for that. Now how does this particular network is connected? If you have observed closely, this entire binary ladder net consists of only 2 values of resistors. Either the resistance is R or it is 2R. There is no other value except R and 2R. So that's the first easy thing to achieve as practically possible. And since the resistances are almost equal at all the nodes, so at all the nodes, if you can see, the resistors are 2R, 2R and 2R. That means all the nodes will have equal currents whenever they are conducting. So that will also take care of the wattage or the current ratio among the various nodes, which was a problem in the previous case. So how is it connected? So it is always terminated with a 2R resistance. What do you mean by termination? Means the last node is connected to ground and it is connected to ground through a 2R resistance, while the intermediate resistances are all R and R, while the node resistances, means to the point where you are going to give the digital values, they are all at 2R. So if this is the arrangement, let us see how this arrangement works out by means of an example. So let us see an example and see what happens if we give a certain value of input voltage. So this is the case. Now let us see if we are going to give an analog input voltage of 1, 0, 0 and 0. Again remember which is LSB and which is MSB in our case. So MSB is going to be here on the extreme right and LSB is going to be here. That's always the first thing that you have to clarify before you start the analysis. So this being the case, only the first node, which is the node D, will be connected to logic high, which could be the supply voltage V, whereas all the other 3 nodes are at ground. Now our job is to find out what is the equivalent analog voltage. Okay. So let us start from this particular node called A. Now at the node A, I am having a resistance of 2R and another resistance of 2R which is parallel to it. So what is the equivalent of parallel resistance? If you connect 2 resistances in parallel and if they are equal, then the overall resistance will be half of that. That means if you have R in parallel with R, the parallel resistance is going to be R upon 2. In this case, we are having a 2R resistance in parallel with a 2R resistance. So the net value is going to be only R. That being the case, we now have a resistance of R which is connected at node A. This resistance is now in series with another resistance from node B, which is R. Now what's the combination of a series resistance? You just add the two resistors. So R plus R becomes 2R. So what is it that you have at B? You have at B which is only 2R. Again you see you have a 2R which is in parallel with another 2R. The resistance is again only R, plus you have series combination of R and you have another 2R. So this way, irrespective of wherever you look, the moment you look to the left of the node, the equivalent resistance is always R. So at the net end of the day, at node C, we are going to have R in parallel with R, which is 2R. So this is the final equivalent circuit that we have for this value of digital input, wherein the node D is connected to voltage V and the other end is connected to ground. Now what is VA? VA is simply the voltage at node D. This we can apply a simple voltage divider rule. What does the voltage divider rule say? The voltage across any resistance is the applied voltage times the value of that resistor divided by the sum of the resistors in series. So applying this simple equation, we get the value of 100 as V upon 2. So this is how we can analyze for a given value. Now just like we have decided that for a MSB, right? This is MSB, this is called as 1 MSB. So for 1 MSB, the value is going to be V upon 2. What about the second MSB? Okay, as expected, the value of the second MSB is to be lesser, right? Because we are converting from digital to analog, second MSB should have a lesser value. So as we can see the analysis forward, the second MSB will have the value which is half of the first MSB. So that we can see here in this table now. Okay, that is shown in this table. Right, there you go. So as per our discussion that we just now done, MSB is going to have a voltage of V by 2. If the voltage is V by 2, then we say its weight is 1 by 2 because V is the applied voltage. Similarly, the second MSB will have its voltage half of MSB. So half MSB is what? V upon 2 divided by 2, which becomes V by 4. Similarly, the third MSB will have half of second MSB, which is V upon 4 again divided by 2, that becomes V by 8. So likewise, we are going to have all the weights going down till we come to V upon 2 raised to n. So the binary weights also change in the order starting from 1 upon 2 for MSB all the way up to 1 upon 2 raised to n for a n bit. So what then becomes a generic expression for any given input voltage, which is the digital voltage. So that is again given by a very similar expression that we had for a variable binary network, variable resistor binary network. The only difference being the denominator is going to be at 2 raised to n instead of 2 raised to n minus 1. The implication is that in case of a binary ladder, the full scale voltage means when all the bits in the digital value are 1, the full scale voltage will never reach the supply voltage. That we will try and see with the help of an example in the next slide. Okay, so let's take an example then and try and see what is it that for a given value of digital, if we are going to use a binary ladder, what is going to be the full scale value and what are going to be the actual cases. So let us take an example of a 5-bit ladder again, which we have done in this case. So the difference here is going to be, okay, let us again try to find out what is the value of the voltage. So this being the case, let us try to find it for a full scale, because my implication is that I am saying that a binary ladder network will never have a full scale value which reaches the supply voltage. So my question is, what is the full scale value? Full scale means what? The binary input is 1, 1, 1, 1, 1. So the digital input to the 5-bit converter is all of them are 1. So if all of them are 1 means what is the actual full scale value? Again we will assume that the supply voltage is 10. So in this case the difference is we are not going to have this minus 1. Okay, this all is going to be the same. Instead of 2 raised to 5 minus 1, we are going to have 2 raised to 5. And instead of zeros, now all these supply voltages will be 10. Why? Because I am looking at all tens, all ones. Okay, so this is going to be the change, and the difference is going to be this one. So if you can see here, for a full scale voltage, all are ones. I have applied the equation divided by 2 raised to 5. Wherever there is 1, I have put 10 volts, and the binary weight 2 raised to 0, 2 raised to 1, 2 raised to 2, 2 raised to 3 and 2 raised to 4, which is nothing but 2 raised to n minus 1, right, because n is 5, so I have to only do up to 2 raised to 4. So if you can look at and do the calculation, this comes to plus 9.6875. If I was using a variable resistor network, I would have got this value as 10. That means in case of binary ladder, the full scale voltage is never going to reach the supply voltage. So that is one outcome or one small difference that we have in this case. But the biggest advantage is we don't have to worry about different values of resistors. We don't have to worry about the different currents in the wings. All the nodes will have the same current. So that's the advantage of using a binary ladder. Now so far we just said that okay, our main job is to do a D to A conversion. But are we doing the D to A conversion? Yes, we are doing. But can this be a circuit now? Yes, it can be, but we need to have a bit more circuitry, which will then be actually called as a D to A converter. So that we're going to see in the next slide. So what does a actual D to A converter have? So let us take the case of an n-bit converter. So what we have studied so far is given over here, which is nothing but our resistive divider network. Okay, we can either choose to have a R to R ladder, which is usually the case. Okay, so we are going to use a R to R ladder. Okay, what are the additional circuitries that we require for this D to A converter? Now remember, the digital data is going to be either ones or zeros, but then they have to be fed into this and they need to have some sort of a storage, okay, which we call as registers, which are nothing but your SR flip-flops. So the input digital data is strobed into the SR flip-flops. By strobed we mean at an appropriate time, whenever you want to do the reading, when okay, like I say, okay, now you do the conversion, now you do the conversion. There has to be a control system which says when to start the conversion process. So whenever the data needs to be strobed, I give the reading pulse. You can see here we are using the both true as well as complement of the inputs, okay, to have a simple SR flip-flop arrangement. So at any point of time, either S is 1 or R is 1. If S is 1, the output will be 1, okay, and then by the help of level amplifiers. Now, you may say, why do we require the level amplifiers? See, at the end of the day, conversion requires to be very precise and as much as possible error free. Now, the applied voltage 10 volt is the most important parameter here. So, we need to have what we call as a precision voltage source. It has to be at plus 10 volts irrespective of whatever is the current you draw, whether it is on load, whether it is off load, whether it is shorted, whatever be the case. So, we usually take the help of level amplifiers. Whenever the flip-flop output is 1, the level amplifier takes the input from the precision voltage and gives that actual 10 volts or whatever is supply voltage to the ladder network. If that particular flip-flop happens to be 0, which happens when S is 0 and R is 1. If S is 0, R is 1, so that particular flip-flop is reset. So I have to now go and ground this input. So that's what this level amplifier does. So net, if you look at this entire D to A converter, it is going to have the input gates, which basically help you to strobe the input into the flip-flops. You are going to have the n-bit data register. You are going to need the level amplifiers so that you give a precise 0 volts or plus V, which is the supply voltage. And finally, you have the resistor divider network that we have studied so far, which is usually a binary ladder. So with that, I think we can understand all these entire components that go into making of a D to A converter. So there are many D to A converters in the market. Now how is that you can characterize them? How is it that you can choose one from the other? So to decide upon which converter to use, you have to do two of the parameters for the D to A converters. That we'll see now in the last slide. So the parameters that we care about as far as D to A converters is concerned is, one is accuracy and the other one is resolution. Now what are these accuracy and resolution? Initially let us understand a bit of definitions, and then we'll take an example, numerical example, and try to figure out what the actual values are for each of these parameters, which enables us to decide which D to A converter to go for. So the accuracy of a D to A converter, it is primarily a function of the accuracy of the precision resistors used in the ladder, okay, and the precision of the reference supply voltage used. Means what? I want to minimize the variations in my analog output voltage, right? Like if the theoretical equation says I am going to get a voltage of 9.5 volts, then I should get 9.5 voltage irrespective of what is the variation in the R and 2R, irrespective of whether my precision voltage source is varying. But reality is that it does vary. You can't have 100% accuracy at all times. There are going to be inaccuracy issues wherever required. Okay, so we can net say accuracy is a measure of how close the actual output voltage is to the theoretical output voltage. Where can the variations arise from? The variations can arise from the variation in the values of resistors R and 2R plus variation in the reference voltage. Even though we are using a level amplifier, even though we are using the reference voltages, there can be variations in supply voltages and it can change. What about resolution then? Now first let us try and define the resolution and then try to take an example of any given converter. Resolution, it defines the smallest increment in the voltage that can be discerned. What does that mean? For example, let us say we are all used to seeing the meters, right? We are able to read the meters. There is something called the least count. So what is the smallest count this particular meter can measure? For example, if I am using a scale, what is the smallest count? The smallest count there is 1 millimeter. Likewise, in this case, the smallest count is 1 LSB. Okay. So resolution, if expressed in terms of voltage, is going to be V upon 2 raised to n or V upon 2 raised to n minus 1 based on which ladder you are using. Whereas if you want to express it as a percentage, just multiply it by 100. So resolution is primarily the function of the number of bits that you have in the digital input signal. So let's take an example there and try to see what are going to be the values of resolution for different different converters. Okay, let us say we have a 9-bit D to A converter and our job is to find out what is the resolution of the 9-bit D to A converter. Okay, so the input given is, it is a 9-bit D to A converter and it uses R to R ladder network. So the full scale voltage is given as 5 volts. Okay, if you have the full scale voltage of 5 volts, now the question asked is you have to find out what is the resolution. Now resolution is nothing but we already said the LSB. What is LSB? LSB is 1 upon 2 raised to 9. 1 upon 2 raised to n if you are using a R to R ladder network. So 1 upon 2 raised to 9 is nothing but 1 upon 512. Now what about the value of this? This is the weight of LSB. What is the value of it? You have to multiply it by the supply voltage. So the supply voltage is going to be, the actual value is going to be 5 upon 512. Okay. So this happens to be around 10 millivolts. So we can say, expressed as a voltage, the resolution is going to be 10 millivolts. Okay. That means this is the smallest count you can measure, the smallest increment your D to A converter can give. Like your values can range from 10 millivolts, 20 millivolts, 30 millivolts, they are all going to be in multiples of 10 millivolts. You can't have 12 or something in between. Then what about if you want to express it as a percentage? If you want to express it as a percentage, you simply have to do the binary weight, not go for the actual value of the voltage. So express it as a percentage, you have to simply multiply it by 100 and that gives around 0.19 or something, which is nothing but around 0.2%. So you can then say the resolution of this 9-bit D to A converter is 0.2%. or if you want to say in value, the resolution is 10 millivolts. So this being the case, what about accuracy then? So let's take an example on accuracy. So if we are having a D to A converter, let us say of it consists of around like let us say it has to give a theoretical value of 10 volts. Okay, for example, let us say if we are having a D to A converter, it has to give me a voltage of 10 volts as per the theoretical calculation. But if my actual output is varying from 9 to 11 volts, what does that mean? I should have been giving 10 volts as an analog output, but either I am giving 9 or I am giving 11 or in this range. So the maximum accuracy that I can get is only 10% because it is plus or minus 10%. So the actual output is 10 volts plus or minus 10%. That means 10 plus 1 or 10 minus 1. So this 10% becomes the accuracy of my D to A converter. If on the other hand, my D to A converter is giving the voltage in the range of 9.9 to 10.1 volts. What does that mean now? Variation is now 0.1 volt on either side, which is nothing but 10 volt plus or minus 1%. So the accuracy now becomes 1%. So accuracy is a measure of how close I am to the theoretical value, and resolution is a measure of LSB. Resolution can be expressed as a percentage or it can be expressed as a volts. Now we can sum up and close this entire topic by trying to do a problem which is reverse. In the sense, I am going to give you a particular value, you are going to decide and tell me what is the bit size that I have to use. That's a very interesting problem. So that if you can understand this problem, that would complete the understanding of D to A converters and how many bits we require for each conversion. So the problem statement that is given is how many bits are required at the input of a D to A converter if it is necessary to resolve the voltages to 5 millivolts. Resolve the voltages means resolution is given as 5 millivolts. Okay, so they are giving the resolution as 5 millivolts. Okay, and it is using a R2R ladder network and it has a 10 voltage full scale, that is your plus V is 10 volts. So resolution is given and you are asked to find what is the value of N. Means is this a 4-bit converter, is it a 5-bit converter, is it a 10-bit converter? We don't know. So we have to figure out and find out. So for this we have to start with definition of what do you mean by resolution, right? So the resolution, as we all know, was given by 1 LSB. So what is 1 LSB? 1 LSB expressed in terms of voltage, not just weights, is the applied voltage times divided by 2 raised to n. N we don't know, but this value is given as 5 millivolts, means 5 into 10 raised to minus 3. Now we can do a bit of simple mathematics and solve for n. What will that be? We are going to have 2 raised to n is going to be 10 upon 5 into 10 raised to minus 3. This comes out to 2000. So if 2 raised to n is 2000, find what is n. You can either apply log on both sides or you can do 2 raised to 1 upon, 2000 raised to 1 upon n, whatever the case may be. So I would prefer to do log. 2 raised to n is 2000, log of 2000. Okay. Right, applying log on both sides. Now this becomes n log 2. So n log of 2 is going to be log of 2000. So if we solve this, eventually you are going to get a value of n which is around 10.97 or something. So we can't take 10.97, we can take it as 11. So that means this particular problem statement, wherein they gave us a resolution of 5 millivolt, gave us a supply voltage of 10 volts, is actually yielding us a converter which is of 11 bits. So the design problem was finding the value of n, we could find the value of n. So in this way we can do back and forth and eventually try to determine what is the resolution, or given a resolution try to find what is the bit size of the converter. So with that we have to summarize this entire session that we have done. We started with the problem of why is it that we require conversion from analog to digital and vice versa. We started with the D to A converters because A to D converters require D to A converters in their architecture. We studied the two ways of doing the conversion using resistor networks. It is a variable resistor and finally the binary ladders. And lastly, we saw the actual setup of a D to A converter, which includes the flip-flop, the load bits and the level amplifiers, and finally 2 parameters which help us characterize any given D to A converter. So in the next session, we are going to start with the A to D converters and see how we use D to A in them. Thank you.